Welcome back to the Chem OG. Today we're going to learn about reaction speed, and we're going to take a look at how fast we can make a reaction happen. And that science is known as kinetics. So reaction kinetics describe the speed with which we can convert reactants to products. And so we're going to take a look at factors that are going to help change or affect how fast it is that we can take a certain set of reactants and convert them to products. And so those factors that are going to determine the reaction speed are, well, we're going to take a look at how well the molecules fit together. If molecules fit together better, then that means we're going to make a reaction happen more quickly. We're going to take a look at how fast the molecules are moving, and we're going to take a look at how far the molecules are from the transition state. And so if we take a look at fit, fast, and far, all of those words start with F, and that gives you sort of a little mnemonic to help you remember what the different things that control the speed of a reaction are going to be. So fit, fast, and far. And so the rate constant K is going to combine those three F's. And so the rate constant is going to be a particular number that's inherent to that reaction based on what reactants we have and how they mesh well together. So if the molecules fit together better, the value of K is going to increase. Okay, so the way we're going to set up our rate constant is that that number is going to be a larger number if the molecules fit together better. And if our molecules are moving faster, that's going to also increase the value of K, because we want K to be a representation of how likely or how probable that reaction is. And so if the molecules fit together better, if they're moving faster, that's going to help increase the value of K. And the farther away our molecules are from the transition state, that's actually going to slow our reaction down. And so having molecules that are very low in energy and they're very, very far from the energy necessary to be able to reach the transition state, that's going to slow our reaction down. And if you remember, when we talk about molecules that have low energy, those are molecules that are also more stable. So stable reactants are going to be much, much slower in producing products than unstable reactants. So K represents the probability the reaction will happen at a given moment. And notice that happening at a given moment represents something that has to do with time, and kinetics always is about how fast or how timely we can make a reaction happen. And so the way expression for K is going to look like this. Seems complicated at first, but it actually includes the three F's that we talked about. So A is the Arrhenius constant, and the Arrhenius constant represents molecular fit. The bigger that number is, the larger the value of K is going to be. Activation energy, or EA, represents how far we are from reacting. R is the universal gas constant, and temperature is the fast term. So again, fit, far, and fast. Those are the three F's that help determine how readily we can make a reaction happen, how quickly we can make it happen, and those all factor into the value of K. And so what are some expressions that use that rate constant, the value of K? So the rate constant pops up in this equation most prominently. The rate of a reaction is equal to the rate constant times however concentrated our reactants are. So depending on our reactant concentrations, we can use those reactant concentrations along with the constant that's inherent to that reaction to be able to figure out the reaction speed. And so mainly what we're concerned with there is we're going to take a look at a snapshot of a reaction, take a look at how many reactants there are, and we're going to use that reactant concentration along with the rate constant in order to be able to determine how fast the reaction is going at that particular moment. And that's what we call an instantaneous rate. Another place that the rate constant pops up is actually in an expression that we can use to be able to determine the equilibrium constant. So the rate constant, what we affectionately call little k, that's what today's lesson is about, is actually not the same thing as the equilibrium constant, or sometimes what's called big K or capital K. So you may be very familiar with the equilibrium constant as being equal to products over reactants. This is an alternate version of the equilibrium constant. And essentially what we're saying here is that K is bigger than 1 And if you remember from products over reactants, if K is bigger than 1, it means products are more likely at equilibrium. Here we're saying that K is bigger than 1 if the chances of forming a product are better than the chances of forming a reactant. And if you think about that, that has to be true because when the reaction comes to equilibrium, it's going to favor the side that is more probable. And so another way of calculating the equilibrium constant is to take a look at the rate constant for the forward reaction, which incorporates the energy barrier moving forward, it incorporates how well the reactants fit together, it incorporates how fast the molecules are moving. We can compare that to the rate constant moving backwards, which takes a look at the activation energy going on the way back, which is not the same as the activation energy moving forward. And it also takes into account, what we have going on the product side and how well the products fit together instead. And so the dynamics on the reactant side aren't necessarily the same as the dynamics on the product side. And whichever side has a higher probability of a successful collision is the one that's going to, influence the equilibrium constant a little bit more prevalently. And so conversely, if K is less than 1, then the chances of forming a reactant are better than those of forming a product. Okay, so as you can see there, the only way that K is going to be less than 1 is if the reaction constant or the rate constant for the reverse reaction is larger than the rate constant for the forward reaction. Thank you so much for watching today's lesson. Please be sure to hit that like button, and if you haven't done so yet, please be sure to support this channel by subscribing. And click on another video. That's a good idea too.